The James Webb Space Telescope, JWST, has captured images of ancient galaxies that are far larger and brighter than expected, challenging our traditional understanding of dark matter. This unexpected discovery has sparked renewed interest in an alternative theory known as modified Newtonian dynamics, (MOND), which offers a fresh perspective on gravity's role in shaping galaxies. In this video, we'll break down Webb's findings, compare them to existing dark matter models, and explore the broader implications for cosmology. So, without further ado, let's dive in. Webb's surprising discovery. The James Webb Space Telescope has provided an astonishing glimpse into the early universe. Instead of detecting small, faint galaxies as expected, JWST has revealed massive, incredibly bright galaxies from this era. These galaxies appear to have formed rapidly and on a much larger scale than predicted by standard dark matter models. According to the Cold Dark Matter Model, CDM, dark matter, a mysterious, invisible substance, gradually pulls in gas and dust over billions of years, allowing galaxies to form through mergers and accretion. This process has been fundamental in explaining the structure and evolution of galaxies observed today. However, Webb's observations suggest that some galaxies in the early universe skipped this slow growth process. Instead, they appear to be fully developed much earlier than anticipated. If galaxies achieved such immense size and brightness so quickly, it indicates a gap in our understanding of galaxy formation. This raises the question, is the dark matter model incomplete, or could an alternative theory, such as MOND, offer a better explanation? Modified Newtonian dynamics. MOND, a new take on gravity. Modified Newtonian dynamics, MOND, is an intriguing alternative to the dark matter hypothesis. This theory suggests that gravity may not always follow Newton's laws, particularly in regions of extremely low acceleration, such as the outer edges of galaxies. While Newtonian gravity successfully explains everyday physics, from falling objects to planetary orbits, MOND proposes that gravitational forces behave differently in weak field conditions. This idea was originally introduced to address the galaxy rotation curve problem. Astronomers observed that stars on the outskirts of galaxies move much faster than expected, given the amount of visible matter. The traditional solution was to introduce dark matter halos around galaxies to account for the extra gravitational pull. However, MOND takes a different approach. Rather than adding invisible mass, it suggests that gravity itself changes in these conditions, providing the additional force needed to explain the observed stellar motions. How MOND relates to Webb's discoveries. If gravity behaves differently in low acceleration environments, it could mean that galaxies form and evolve faster than previously believed. This could explain why JWST is detecting massive, fully formed galaxies in the early universe, structures that the dark matter model would predict to grow more gradually over time. However, MOND is not without its challenges. While it works well in explaining individual galaxy rotation curves, critics argue that it struggles to account for larger cosmic structures, such as galaxy clusters, as effectively as the dark matter model. Additionally, MOND does not yet provide a unified framework that explains all cosmic phenomena as comprehensively as dark matter theory. Despite these challenges, Webb's discoveries have prompted some astronomers to reconsider MOND, especially since its predictions align closely with observations of rapid galaxy growth. While MOND may not fully replace the dark matter model, its success in explaining certain galactic behaviors keeps it a relevant and compelling alternative. Beyond MOND. Tensor vector scalar gravity, TeVS. These findings also bring attention to another alternative theory, tensor vector scalar gravity, TeVS, developed by physicist Jacob Bekenstein in 2004. TeVS builds on MOND while addressing some of its limitations, incorporating additional tensor, vector, and scalar fields to describe gravitational interactions in a way that aligns more closely with Einstein's general relativity. TeVS offers a more comprehensive framework for explaining galactic motion without relying on dark matter. If this theory can accurately describe the growth of the early massive galaxies detected by Webb, it could provide a powerful alternative to current dark matter models. What comes next? The implications of these discoveries are profound. They challenge one of the core pillars of modern cosmology, the dark matter paradigm. Since dark matter was first proposed, it has served as the leading explanation for unexplained cosmic phenomena, shaping our understanding of galaxy formation, galaxy clusters, and large-scale cosmic structures. However, if galaxies in the early universe could grow without dark matter, it may suggest that dark matter is not as universal as once thought. This fuels the need for further research and observations. Future telescopes, such as the Vera C. Rubin Observatory, are expected to come online soon, offering even more data on galaxy formation across cosmic history. Meanwhile, JWST will continue to peer deeper into the universe, helping scientists determine whether these rapidly growing galaxies are common or exceptional cases. By closely studying these structures, researchers can rigorously test MOND, TeVis, and the dark matter model, refining our understanding of the cosmos. Final thoughts. The James Webb Space Telescope is revolutionizing our understanding of the universe, raising questions about the role of dark matter and the fundamental nature of gravity. Whether the answer lies in dark matter, MOND, TeVis, or an entirely new theory, one thing is clear: our understanding of cosmology is far from complete. Thank you for watching. If you're as fascinated as we are by these groundbreaking discoveries, be sure to subscribe and stay tuned for more cosmic explorations. Let us know your thoughts in the comments. What do you think about MOND and the dark matter debate? The James Webb Space Telescope has captured images of ancient galaxies that are far larger and brighter than expected, challenging our traditional understanding of dark matter. This unexpected discovery has reignited interest in an alternative theory known as modified Newtonian dynamics, MOND, which offers a new perspective on gravity's role in shaping galaxies. In this video, we'll break down Webb's findings, compare them with the MOND theory, and explore their broader implications for cosmology. So without further ado, let's dive in. Webb's latest observations provide a surprising view of the early universe. Instead of detecting the small, faint galaxies predicted by current models, it has revealed massive and incredibly bright galaxies from this period. These galaxies appear to have formed much more rapidly and on a larger scale than the standard dark matter model suggests. According to the cold dark matter model, an invisible and mysterious form of matter plays a crucial role in galaxy formation. It exerts a gravitational pull on gas and dust, gradually assembling galaxies over billions of years through mergers and material accumulation. This model has been central to cosmology, helping explain the shapes and structures of galaxies observed today. However, Webb's findings challenge this conventional understanding. The massive, luminous galaxies it has detected seem to have bypassed the slow growth process that dark matter models predict. Instead, they appear fully developed much earlier in the universe's timeline. If these galaxies reach their impressive size and brightness so quickly, it suggests that something fundamental is missing in our current models. Either the dark matter theory is incomplete, or an alternative explanation, such as MOND, might provide a better fit for these observations. Modified Newtonian dynamics. MOND, a possible alternative. Modified Newtonian dynamics, MOND, offers an intriguing alternative to dark matter. This theory proposes that gravity doesn't always behave as Newton's laws suggest, especially in regions of extremely low acceleration, such as the outer edges of galaxies. Newtonian gravity has long been the foundation of physics, explaining everything from falling objects to planetary orbits. However, MOND suggests that in conditions of weak gravitational pull, gravity operates differently than expected. This idea was originally developed to address the galaxy rotation curve problem, the observation that stars at the outer edges of galaxies move much faster than they should, based on visible matter alone. The traditional solution to this discrepancy was to introduce dark matter, an invisible halo surrounding galaxies, adding the extra gravitational pull needed to explain these high speeds. MOND, however, offers a different approach. Instead of relying on unseen matter, it proposes that the laws of gravity themselves are modified in low acceleration environments, providing the additional force necessary to sustain the rapid motion of stars. This theory is particularly relevant to Webb's discoveries. If gravity behaves differently at the edges of galaxies, it could mean that galaxies form and evolve faster than traditional models predict. This might explain why Webb is detecting massive, fully developed galaxies in the early universe, where dark matter models would expect much smaller, gradually growing structures. Challenges and debate. Despite its potential, MOND faces significant challenges. Critics argue that while it explains the motion of individual galaxies well, it struggles to account for larger cosmic structures like galaxy clusters. Additionally, MOND has yet to be integrated into a broader framework that explains all cosmic phenomena as effectively as the dark matter model does. Nevertheless, Webb's recent findings have led some astronomers to revisit MOND, especially since its predictions align closely with the newly observed rapid galaxy formation. While it remains uncertain whether MOND could completely replace the dark matter model, its success in predicting certain cosmic behaviors, such as galaxy rotation curves, keeps it a compelling and relevant alternative.